Awesome, we're rolling. So today we'll look at a problem from the Virginia Tech Regional Math Competition in 1979, problem 4. It basically states that let f of x be a continuously differentiable function on the closed interval 0 to infinity, and suppose that the limit as x approaches infinity of f prime of x equals 0. So we have to prove that the limit of x approaches infinity as f of x over x approaches 0. Well, upon first seeing this problem, this gives me the intuition to think of f of x approaching a constant. So we have that as the limit as x approaches infinity, f prime of x approaches 0. If I actually try to look at some functions that exhibit this behavior, an immediate function that comes to my mind is the function f of x equals 1 over x. So if I were to graph this, exclusively graphing on the interval 0 to infinity, this sort of exhibits a curve like this, where this is y, this is x. And as we approach 0 from the right-hand side, we approach positive infinity, and that's pretty easy to understand. I mean, if you have 1 divided by 0.0001, you're going to get a really big number. And as you approach infinity, the denominator becomes so large that effectively the fraction is nearly 0. But here we want to prove that the statement, the limit as x approaches infinity of f of x over x approaches 0. So if I know that the limit of my derivative as x approaches infinity equals 0, but what does my derivative tell me? The derivative tells me the instantaneous slope. Slope at any point of the function. So I basically know that as my limit approaches infinity of my derivative approaches 0. So that means that the rate of change of my function approaches 0. So if my rate of change of my function is 0, essentially I'm approaching a constant value. So this gives me the motivation that, and this is also really easy to tell, so you could say that if limit x approaches infinity of f prime of x approaches 0, you could sort of integrate both sides, and you can also conclude that the limit as x approaches infinity, f of x approaches some constant c. And c could be anything. It could be a million, it could be a negative million, it could be any sort of thing. Because we could approach a constant from decreasing slope, or we can approach that constant with an increasing slope. And what I mean by this is that we could have a graph that looks essentially something like this, where the slope is negative at each point, and then it basically turns out to be 0. So it's a decreasing function. Or you can have some sort of like an increasing function that approaches the constant limit like this. And it doesn't always have to be this shape. It could be some sort of an oscillating function like this. But eventually, we know that the rate of change becomes 0. So it has to sort of exhibit this sort of regression to this line C. So we know that either way, as I approach infinity, since the rate of change of my function is C, as I approach infinity, f of x approaches some constant C. I could basically say that the goal limit is basically, so I know this sort of approaches a constant C, but x approaches infinity. And one of the first things you would learn in Calc 1 when we're talking about limits is that if a function on the top approaches some sort of constant and the bottom function approaches plus or minus infinity, essentially the entire limit would approach 0. And that makes sense, right? Like if you have any sort of constant c, but you're approaching infinity, well, it doesn't matter what constant I have. Even if I have a billion over infinity, that's still 0 because infinity is just so big. It's not even like a number that you can sort of conceptualize. So if I have any sort of number on the top here, whether it be 1, 2, or any sort of number, and the bottom function is an increasing function that approaches infinity or a decreasing function that approaches negative infinity, essentially I approach the same value, 0. Well, that proves the desired question.